This is an overview of Lecture 9, and in Lecture 9, we're going to focus primarily on the differences for two means when the samples are independent. Two samples are independent if the sample values from one population are not related to or somehow naturally paired or matched with sample values from the other population. Otherwise, the samples are dependent. And again, we're going to focus our study to independent samples. An example of dependent samples would be this. Suppose I gave you a pre-test on Chapter 9 and then a post-test on Chapter 9. So I would have two sets of scores for you. I would have a score that you earned prior to learning Chapter 9, and then I would have a score that you earned after learning Chapter 9. And those would be dependent samples because they are connected to you. But for the purpose of this lesson, we will focus on independent samples. Example 1, do men talk less than women? The table below shows the results from a study of the number of words spoken in a day by men and women. And the original data are in data set 17 in Appendix B of your textbook. We're not going to worry about that. Use a 1% significance level to test the claim that the mean number of words spoken in a day by men is less than that for women. So they did a study, and the study involved 186 men and 210 women. And they found that the average number of words spoken by men in a day is 5,668.5. And the average number of words spoken by a woman on average in a given day is 16,215. The standard deviation for men, 8,632.5, and the sample standard deviation for the women, 7,301.2. Now, to do the comparisons to see if there is a difference. Now, on the surface, there appears to be a difference because women on average is higher than men. For example, if you look at the women, 16,215 is definitely larger than 15,668.5. This might lead you to conclude that women do speak a lot more than men, but do we really know that? Maybe the sample wasn't quite as good as it needed to be. Maybe if we used another set of men and women and compared averages, maybe we wouldn't get the same thing. Maybe we would find out that on average in that situation, the men talked more than the women. But we're going to take the data set that we have and we're going to assume that the study was done with appropriate randomization for the samples. We're going to see if the difference between the two populations is significant enough to make the claim. Notice that we're testing the claim that the mean number of words spoken in a day by men is less than that for women. We're going to use the two-sample t-test. You'll go to Stat Tests, and you'll select two-sample t-test. Why two-sample? Because we have two samples. We have a sample of men and a sample of women. And why is it a t-test? Because we are looking at averages. We're looking at means. So two-sample t-test. And we have the summary stats. We do not have the raw data, so we will select stats. And then we will just put in the appropriate calculations. Now, please be aware that the order of the information in the table may not be the same as the input order on the calculator, so double check to make sure that you're actually entering things in the right section. And for this class, we will always choose no when they ask if it is a pooled situation here for the standard deviation. So part A says to identify the null and alternative hypotheses. And the null is going to claim that the difference in the average with the men and the women is actually non-existent. The difference is 0, or the averages are the same. And since it's a test to determine if men talk less than women, the alternative will say that U1 is less than U2, which makes it a left-tailed test. To calculate the test statistic, we will use, again, the two-sample t-test with pooled no. And again, since we're using summary stats, we select stats. I guess that's somewhat redundant, but I want to make sure that you are clear about how to run this particular test. And once you run the data, you should get a test value of minus 0.68. Question is, does this seem extreme? Well, minus 0.68 is not even one standard deviation from the mean, so it does not seem to be extreme. What is the p-value? The p-value is 0.25. Is this less than the alpha level? Well, the alpha level, if we go back and look at the problem, the alpha level is 0.01. It's a small alpha level. But our p-value is 0.25. So the p-value is actually greater than the alpha level. So the answer to this would be no. And since the p-value is greater than the alpha level, we will fail to reject the null, which means we cannot conclude that men talk less than women. F. Write the confidence interval for this data using two-sample t-interval. Well, if the alpha level is at 1%, the confidence level would have to be 99%, which is 1 minus the alpha level. So go ahead and run the two-sample t-interval. Make sure you use 0.99 for the confidence level. And you will get the confidence interval, and notice that 0 is in the interval. Well, 0 is what the null claimed, right? If you go back up here, the null claimed that the difference in the averages between men and women is 0. And 0 is captured between negative 2641 and positive 1548.3. So since 0 is in the interval, then again, we would fail to reject the null. Example 2. Do men have a higher mean body temperature? The data set for this study is found in data set 3 and so forth. And in this situation, we're comparing men and women, and we're looking at their body temperatures. The number of men in the study, 11. The number of women, 59. And the average temperature for men, 97.69 degrees Fahrenheit, with a standard deviation of 0.89 degrees Fahrenheit. And for women, the average temperature, 97.45, with a standard deviation of 0.66 degrees Fahrenheit. Well, if you look at the data, if you look at the table as is, it appears that men have a slightly higher temperature than women. And again, is it because of the sample? In other words, if we had gone out and taken maybe a larger sample, or if we conducted a different study, or excuse me, the same study with a different group of men and women, would the results be the same? Probably not. So just because it appears that men do have a slightly higher temperature than women in this situation, is the difference significant enough? And that's what we're going to have to decide. So we will use the two-sample t-test. We will enter the data. And again, the order that the values appear in the table may not correspond to the order for the calculator entry. So watch your step there. Again, the null is going to claim that the mean temperature, the mean temperatures are the same, and that the difference is 0. And in this case, we're looking at different. Do they have different body temperatures, not greater than or less than? And we will use the two-tailed test. We will select not equal to. mu1 is not equal to mu2. And like before, we will run the two-sample t-test. We will make the pooled no. Make sure we select mu1 is not equal to mu2. Once we run it, we get a t-value of 0.85. And 0.85 does not seem extreme. It's still less than 1 standard deviation from the mean. And the p-value is 0.41. Is this less than the alpha level? Well, 0.41 is greater than the alpha level. And again, since p is greater than alpha, we will fail to reject the null, which means we cannot conclude that men and women have different body temperatures. If you use the two-sample interval, you capture this interval, and one side is negative and the other side is positive, so obviously 0 is contained on the interval, which again justifies our failing to reject the null. Because remember, the null claims that the difference in the temperatures is 0, and 0 is in our confidence interval. Now, what happens if you are given raw data? In example 3, we have the raw data. We have the weights for yellow and brown M&Ms. Before we can run the test, we actually need to put the weights for the yellow M&M in list 1 and the brown M&Ms in list 2. And once we put all of that information into lists 1 and 2, we will run one variable stats twice. We will run it once for L1, and we will write down the summary statistics, and then we go back and run it for L2, which will give us the statistics for the brown M&Ms. Now that you have this information in table form, you can run the test just as we did in examples 1 and 2. I will leave it up to you to decide whether or not there's a difference in the weights between yellow and brown M&Ms. Example 4, proctored and non-proctored tests. Suppose a random sample of seniors is divided into 2 groups to take a final exam. One group is proctored, which means they are under a teacher's supervision, and the other group is non-proctored, which means there is no teacher present. We're going to use a 1% significance level to test the claim that the samples are from populations with the same mean. Well, here's the summary stats. The non-proctored students, we had 32. They had an average of 88.62 with a standard deviation of 22.09. And the proctored group, which means they had a teacher, walking around and giving them the old evil eye if they tried to look at their neighbor's paper and so forth. We had 30 students in there, and they scored on average 74.3 with a standard deviation of 12.87. If we look at this, distribution, it appears that those who were in the non-proctored group scored a lot higher. We don't really know why. We could assume that maybe they cheated, or maybe they were under less stress without a teacher present. We shouldn't really draw conclusions like that. That's not what we're really concerned about. We're concerned about whether or not the differences or the difference in the scores is actually significant. If we run the two-sample t-test and we select stats because we have the summary stats, we enter the data appropriately and carefully. We choose no for pooled. We will get a p-value of 0.003. Well, that is less than the alpha level. 0.003 is less than 0.01. Therefore, we would have to reject the null, which means that there is no difference. Excuse me, that there is a difference in the averages. Let me rephrase that again. I just read the problem a second time here. We're going to reject the null, which means we do not have enough information to conclude that the averages are the same. It appears that they are different after all. So maybe the ones who were in the non-proctored group did cheat, or maybe there was just less stress there, therefore they scored higher. Again, when doing hypothesis testing, we're supposed to stick to the subject at hand. And all we really wanted to know was whether or not the difference in the means was significant, and we determined that they are, that the difference is significant. We could solve by hand. Obviously, the calculator is a much more efficient way to draw the conclusion. But what I did here was I wanted to show you that it is possible to do the calculation by hand. And at first, when you look at this formula, it appears to be somewhat intimidating. But if you think about it, it looks a lot like one that we saw in previous lectures. Remember when we found z-scores? We would always take the x data value and we would subtract from that the mean, and then we would divide by the standard deviation. Well, it's the same concept, except now we have two groups to worry about. Now, remember, the null hypothesis is going to claim that the difference in the means is 0, which is why we have a 0 here. But what we do is we take the two means, 88.62 and 74.3, and we subtract those, and then we divide by the variance over the number for each situation. So 22.09 squared over 32 plus 12.87 squared over 30. And as you can see, we still get the same test statistic that we got earlier. Okay. And by the way, if you have a t-value of 3.1421, and you want to figure out the p-value, simply do the t-CDF, and since we're starting on the right tail, we will do 3.1421 up to 5. Degrees of freedom has to be 29. Because in this case, we take the smaller of N1 and N2, and we just subtract 1. So if you go back to the original data here, the smallest N is 30. One of the N's is 32, one is 30. We take the smaller and subtract 1, and that gives us 29 for degrees of freedom. And once we run that calculation, we will double to get the p-value because this is a two-tailed test. And if you look at my answer here, it is slightly different from the one calculated prior. And that is because of rounding error. I rounded a little low because I didn't want to go beyond 2 decimal places. Honestly, if I were taking a test and I had to show my work and do the calculation by hand, I would probably go out about 4 decimal places instead of 1 or 2.